Welcome to another deep dive. We're going to be tackling,
Oh, this is a fun one.
yeah, this is a fun one.
Yeah.
Einstein's theory of special relativity. And you've sent us some really fascinating sources, I have to say. We've got textbook chapters, a casual conversation about relativity, and we even got some Indonesian text in here.
Wow. Yeah, that's really interesting. It really shows how these ideas, I think, really capture the imagination no matter where you are in the world.
It really does.
Yeah.
So our mission today is to try to break down special relativity and kind of explore what makes it so groundbreaking.
Right.
And hopefully have some fun along the way. It's, one of those things that I think can seem really intimidating at first glance.
So absolutely.
I noticed even in that Indonesian conversation, those students were kind of wrestling with some of the same questions that I had when I first learned about this stuff.
It's true.
Yeah.
Yeah, special relativity really challenges a lot of our everyday intuitions about how the world works. But before we get to Einstein's, mind-bending contributions, we actually need to start with something a little bit more familiar. Galilean relativity.
Okay, Galilean relativity. Okay, that sounds a little less daunting.
Yeah.
What's that all about?
So that's just the way we typically experience motion in our daily lives.
Okay.
Think about it this way. You're on a train, okay?
Okay.
And the train is moving smoothly at constant speed.
Right.
Inside the train, everything feels stationary to you, right?
Right.
You can walk up and down the aisle.
Yep.
You can toss a ball to a friend.
Uh-huh.
It all seems normal.
Right.
But to someone standing outside watching the train go by,
Yeah.
you and everything inside the train are in motion.
Yeah. That makes sense.
Yeah.
It's like how a car traveling at 60 miles per hour feels still to the driver.
Exactly.
But to someone standing on the side of the road, that car is zooming past.
Exactly.
Yeah.
So your speed is always relative to something else.
Yeah.
That's the essence of Galilean relativity. And this brings us to the concept of what we call inertial reference frames,
Okay.
which is basically just a fancy way of describing
Yeah.
systems where objects at rest stay at rest and objects in motion stay in motion at a constant speed and in a straight line.
Got it.
Okay. Like our train moving at a constant speed,
Okay.
that's an inertial reference frame.
So both the Galilean relativity and Einstein's special relativity
Yes.
deal with these inertial reference frames.
Yes. They both start with that same basic idea.
Okay.
But here's where things start to get really interesting.
Okay.
One of your textbook excerpts highlights a key difference,
Okay.
the speed of light. And it says that light travels at the same speed,
Hmm.
no matter how fast the observer is moving.
Wait. Really? That doesn't seem right.
Right.
If I'm walking towards a beam of light, wouldn't it seem like it's coming towards me faster?
That's what we would intuitively expect
Yeah.
based on our everyday experience.
Yeah.
It's like if you're on that train again and you're tossing a ball to your friend, to you, the ball might seem to travel at a certain speed, but to someone standing on the platform, the ball's speed would actually appear faster because it's also moving along with the train.
Right.
So why is light different?
Yeah, I don't get it. What makes light so special?
Well, that's the question that puzzled physicists back in the late 19th century.
Okay.
They had what are called Maxwell's equations,
Ooh.
which are basically a set of fundamental laws that describe how electricity and magnetism work.
Okay.
And those equations predicted that light always travels at this specific speed, represented by the letter c.
Okay.
Which is about 670 million miles per hour.
670 million miles an hour. That's incredibly fast.
It is. And according to Maxwell's equations, this speed is constant, regardless of the observer's motion. But that created this conflict with the way we normally think about motion.
Right.
Like in our train example.
Right. Because if the laws of physics are the same for everyone, no matter where they are or how they're moving, and those laws say light speed is always c.
Right.
Wouldn't that mean?
It means that light must travel at c for everyone.
Wow.
No matter how fast they're moving relative to the light source.
That's where it starts to feel like my brain is melting a little bit.
Yeah.
So how did Einstein resolve this?
Well, Einstein's genius was in accepting this seemingly paradoxical truth
Okay.
about the speed of light and building his theory around it.
Yeah.
And to make it work, he realized something truly revolutionary. Time itself must be relative.
Hold on. Relative? You mean time isn't constant? This is getting weird.
It is weird.
Yeah.
But it's weird in the most amazing way. Think about it this way.
Okay.
If the speed of light is truly constant for everyone,
Okay.
no matter their motion,
Right.
but distances can seem to change based on how fast you're moving.
Okay.
The only way that can be true is if time itself
It's
also affected by your motion.
I'm trying to wrap my head around that.
Yeah.
So you're saying that time isn't this absolute fixed thing that we all experience the same way?
Exactly. And one way to visualize this is with this thought experiment.
Okay.
Imagine you're standing still, watching a beam of light travel from a tree to a lamppost.
Okay, got it.
Now imagine someone else is zooming past you at close to the speed of light, also watching that same beam of light.
Okay, I'm picturing it. They're both seeing the same light beam.
Right. But here's the key. Because the speed of light is constant for both of you,
Okay.
but your perception of distances might differ because of your relative motion.
Right.
It means that your measurements of the time it took for that light to travel would also have to be different.
Wait, so the person zooming past would actually measure a different amount of time
Exactly.
for the light to travel than I would?
Yeah, exactly. And that difference in time measurement is what we call time dilation.
Wow. Oh, my mind is officially blown. So time itself can actually stretch or compress depending on how fast you're moving.
Yeah, it's not that the clocks are broken. It's about the flow of time itself being experienced differently depending on your reference frame.
That's wild.
Yeah, and that's one of the most mind-bending consequences of special relativity.
So are we saying time travel is possible?
Well, time dilation doesn't quite work like time travel in the science fiction sense, but it does mean that time as we experience it is not as absolute as we might think.
Okay, that's definitely going to take some time to sink in.
Yeah.
But I'm hooked.
All right.
What else can you tell me about this theory?
Well, now that we understand how time is affected,
Right.
let's explore another fascinating consequence of special relativity.
Okay.
Length contraction.
Length contraction. Okay, that sounds intriguing. Is that like objects shrinking when they move really fast?
That's the basic idea. It's another one of those concepts that seems counterintuitive at first.
Right.
Imagine a spaceship traveling at a significant fraction of the speed of light relative to an observer on Earth.
Okay, I'm picturing it.
Yeah.
A sleek spaceship zooming through space.
Now, to that observer on Earth, the spaceship would actually appear shorter in the direction of its motion than it would if it were at rest.
Wait, really? So it's not just time that gets warped, but space itself.
Exactly. Special relativity tells us that space and time are intertwined.
Wow.
And they're both affected by relative motion.
Okay.
And it's not an optical illusion either. The spaceship physically contracts in length.
Wow.
From the perspective of the stationary observer.
So if I were on board that spaceship, would I notice it getting shorter?
Nope. To you, everything inside the spaceship would feel perfectly normal.
Okay.
Your own measurements of the spaceship's length wouldn't change.
Right.
It's only from the perspective of an observer in a different reference frame, like someone standing on Earth.
Okay.
That the length contraction would be apparent.
That's so wild. It really makes you rethink everything you thought you knew about reality. So we've got time dilation, length contraction. What other mind-blowing consequences does this theory have?
Well, there's one more we should definitely discuss. Okay.
The famous equation ETCS.
Ah, yes. EMTF, everyone's heard of that equation.
Yeah.
But I'll be honest, I'm not entirely sure I understand what it actually means.
It's probably the most famous equation in all of physics.
Yeah.
And it's a direct consequence of special relativity.
Okay.
What it tells us is that energy, represented by the letter E, and mass, represented by the letter M, are fundamentally equivalent.
Okay.
And they're related by the square of the speed of light.
Yeah.
What is the mass?
So you're saying that mass can be converted into energy and vice versa?
Precisely. And this has huge implications.
Yeah.
It explains how stars like our sun generate energy through nuclear fusion, where a tiny amount of mass is converted into an enormous amount of energy.
Oh, wow.
And it also explains the destructive power of nuclear weapons, where the splitting of atoms releases a tremendous amount of energy by converting a small amount of mass. That's incredible. It's amazing to think that this seemingly simple equation has such profound consequences for our understanding of the universe, you know, from the smallest atoms to the largest stars. But back to time dilation for a moment.
Yeah.
Does it actually have any practical applications in our daily lives, or is it just a theoretical concept?
It actually does have practical applications.
Okay.
And one of the most important is in GPS technology.
Really? GPS. I use that all the time.
Yeah.
How does special relativity play a role there?
Well, GPS satellites orbit the Earth at very high speeds, which
Okay.
means they're experiencing time dilation
Relative to us.
relative to us here on the surface.
Up here, yeah.
So time runs a bit slower for the satellites
Mhm.
than it does for us.
So even though it's a tiny difference, it's significant enough to affect GPS readings.
Absolutely. If we didn't account for the time dilation predicted by special relativity,
Yeah.
GPS systems would quickly become inaccurate.
Wow.
You know, imagine your GPS telling you you're miles away from your actual location.
Right.
So engineers actually have to make adjustments to the satellite clocks
To compensate.
to compensate for this relativistic effect.
Wow, that's fascinating. I never realized that something as commonplace as GPS relies on such complex physics. So this seemingly abstract theory actually has a very concrete impact on our daily lives. And what's so amazing is how special relativity forces us to rethink our fundamental assumptions about reality.
It's true. It tells us that space and time aren't separate absolute entities, but rather they're interwoven
Right.
and relative to the observer.
Yeah.
And this has profound implications not just in physics, but also in fields like cosmology and philosophy.
It's like reality itself becomes more fluid and less rigid than we always assumed. It's incredible how a theory developed over 100 years ago can still be so relevant and mind-boggling today. And speaking of mind-boggling, one of your textbook sources ends with a really thought-provoking question about the deeper meaning of time being relative. What does it really mean, and what are the philosophical implications for how we understand our existence in a universe governed by these rules?
Yeah, it really makes you think, doesn't it? If time isn't this absolute unchanging thing that we
Right.
perceive it to be, then what else might we be wrong about? Like, what does it mean for our understanding of, like, the past, present, and future
Yeah.
if time is flexible in this way?
It challenges our very notion of reality, doesn't it? I
Yeah.
mean, we're so used to thinking of time as this linear progression,
Right.
but, special relativity suggests it's much more nuanced than that.
It really does. And, it's like suddenly the universe feels so much bigger
Yeah.
and more mysterious. And I have to say, even diving into these concepts, even with the explanations and the examples,
Yeah.
it's still a lot to absorb.
Oh, absolutely.
Yeah.
It took, the greatest minds in physics decades to really grapple with these ideas
Right.
and develop the theory. But that's part of the beauty of scientific exploration.
I know, it's so cool. Isn't it? There's always more to learn,
Yeah.
always deeper layers to uncover.
And speaking of uncovering, we haven't even touched upon some of the more philosophical implications
Yes.
of special relativity. Like, what does it mean for concepts like free will or destiny if our experience of time is relative?
That's getting into some really deep territory.
We know.
But you're right. Special relativity really does raise all sorts of fascinating questions that extend beyond the realm of just physics. It makes you wonder about the nature of perception, consciousness, even the meaning of existence itself.
It really does. I feel like we could talk about this for hours.
Me too.
And I don't know about you, but I'm definitely walking away from this deep dive
Yeah.
with a whole new perspective on the universe and my place in it.
I think that's the best outcome we could hope for.
Yeah.
It's not about memorizing equations or facts. It's about sparking that curiosity and wonder and encouraging people to question their assumptions and engage with these incredible ideas.
Yeah. I love that. Well said. And to our listener, we hope this deep dive into special relativity has left you with a sense of awe
Absolutely.
and maybe even a little bit of that mind-bending feeling that we've been talking about.
And if this deep dive has left you hungry for more, remember, there's always another layer to peel back, another mystery to explore
Yeah.
in this vast universe of knowledge.
It's true.
Keep questioning, keep learning,
Love it.
and keep looking up at the stars.